Well, hello everyone. Let's talk about some random vibration. Lots of different names for vibration testing that you might come across: acceptance, reliability, development testing, durability testing, qualification testing. Sometimes you hear the words proto-flight testing with satellites. They all really mean the same thing. We're going to strap something to a shaker and we're going to find out if it's going to survive. Now, generally, random falls into this 20 to 2000 hertz range. That's what you typically find for these type of specifications, as opposed to some other, like sine time waveform replication is generally lower in frequency. Shock is absolutely higher in frequency. We're putting in an impulse into the system in some way, and of course, impulse functions have this property of having infinite frequency content. So shock can go to really high frequencies. But again, we're going to talk about random today, and that falls in very typically this 20 to 2000 hertz range. And really crucial is determining what our boundary conditions are for the test and trying to replicate those when we attach our test article to the shaker. The basic idea with the vibration test is what we're going to do is we're going to figure out the system transfer function, and then that transfer function is going to be used for control. So we run what's called a pretest or system identification, and then that signal gets used as a basis for the first drive signal. And very basically what happens is we send out some voltage signal to the shaker, we measure the response, and this happens open loop. We're just putting a signal out and we're letting the shaker do whatever we want. It's basically performing a quick modal test before we get started. And then we have that input signal over the output signal, and we end up with a transfer function in G's per volt. And then what we do is we invert that transfer function, okay? And we have this initial drive. We know the transfer function. We take that times the target, and we end up with the drive, right? So again, the signal maybe is, this equation maybe a little backwards, right? Because we measure the signal, we multiply by our transfer function, and that's where we end up back with the drive. And for random, this all happens in the frequency domain. Unlike sine, which is a time domain method for control, random is a frequency domain method, which carries its own difficulties to it. So again, I mentioned sine. Sine is very typically kind of easy to understand. We output a single frequency at a time and sweep that, so we constantly change the frequency over frequency range. Random control, at least for me, took me a little longer to get my head wrapped around. It's all the frequencies all at once that go out to the shaker. The thing that helped me kind of wrap my head around this was an analogy by a fellow named Wayne Tustin, who was a guy that did a lot of vibration testing instruction and stuff. And his analogy was you're watering a whole bunch of plants. Okay, you have a whole bunch of plants out on your porch. You're going to water all of them. Sine testing, you spray in each pot a specific amount of water, and you know how much water has gone into each pot. Random is like putting a spray nozzle at the end of your hose and spraying all the plants all at once. We know how much water is coming out of the hose and gets delivered out to the plants, but we need to take some kind of statistical analysis because we're not sure at any particular instant in time exactly how much water is going into a particular pot. All we can do is take a number of averages and say, okay, over a specified amount of time, statistically, this is how much energy went in. Again, sine, one frequency at a time, random, all the frequencies all at once. The next thing to talk about is self-check, also called system identification in our software. And any vibration controller is typically doing this kind of setup. Our first step in a self-check is measuring background noise. Then we build up this drive, so it's between the min and max drive levels. And what we're doing here is looking at this signal to noise ratio. Okay, and that's programmed in the software. We want to have a drive level that meets or exceeds our minimum signal to noise ratio. Once we get to that level, we start to measure the system ID, i.e. we start to take averages here of this self-check drive, and that's used to calculate our transfer function and also coherence. After the averages are complete, this ramps down, we do some calculations here, and one of the calculations is this open loop threshold. We're also looking at all the measurement channels to determine if they meet the minimum signal to noise ratio. If they don't, you'll get an open loop error message. Now, just a caveat there, sometimes open loop is not a bad thing. You might, for instance, if you're using a laser to measure displacement during a vibration test, you might get an open loop error on the laser, but it might be because the laser is measuring for a particular resonance that might occur at a particular frequency, and we don't have significant enough amplitude during the pretest to hit that resonance enough that the laser can register the displacement. So there's situations like that where open loop might not be a bad thing, but 99% of the time, if you have something that comes up as open loop, you want to investigate that. Then after that, using the measured transfer functions, we can extrapolate what the responses are going to be, and then we report out those responses and their maximum levels. And we'll look at our system verification tool that gives you a lot of that information. So random covers an entire bandwidth for a specified period of time. At a bare minimum, to run a random test, you need random PSD breakpoints, which come in pairs of amplitude and frequency. You need to know the duration at full level. And there's some optional parameters such as degrees of freedom, which may or may not be specified in a test plan. And we'll talk about what that means as well. The idea, though, here is that random is going to be a good representation of the operational environment the product's going to be in. So again, can't stress that enough. That has to make sense. You might be familiar with this, you might not, but when you do an FFT, there is a minimum amount of sampling time that's required. And the discrete Fourier transform has this relationship between the delta frequency of the frequency domain data and the minimum amount of time you need to sample to get that frequency resolution. And it's an inverse relationship. For an example, if you have a 4 Hertz resolution, okay, you need a quarter second of time data in order to do that discrete Fourier transform. If you have 1/8 Hertz resolution, you're going to need an 8-second long minimum amount of time to do that discrete Fourier transform. Reason this is important is we typically have our frequency resolution for control in random somewhere between 2 and 4 Hertz. That puts us between a half a second and a quarter second per block or frame of data that we need to process into a PSD and average together. If you're doing a vibration test, at a bare minimum, the control loop time is going to be the inverse of the frequency resolution. You can run into issues if you try to get too fine a frequency resolution because your loop time starts to get much, much longer. And a quarter second versus 8 seconds is an eternity of difference in a vibration test. A lot can happen in a vibration test in 8 seconds. Now, that paired with the exponential averaging that's used in the control loop gets you significantly longer times, right? So if you look at your control setup, and you can specify this, there's an averages per loop and an exponential weighting factor. By default, they're set to 5 and 5, but at a bare minimum, that means if you're taking 5 averages and you have like 1/8 hertz resolution, which is an 8-second long time block, you're going to end up with a 40-second long averaging process, then that exponential weighting factor. So you're going to take significantly longer than, let's say, a 4 hertz resolution, which is a 1/4 second, which means it's 1 1/4 second for a control loop. 1 1/4 second versus 40 seconds is a big, big difference. We have a thing called degrees of freedom in random control. And degrees of freedom is not mechanical degrees of freedom, but statistical degrees of freedom. With a stable average, the degrees of freedom are equivalent to the number of blocks that you put into an average multiplied by 2, because we have a real and imaginary portion. So that's for measurement channels. We typically use linear averaging, but for the control channel, we always use exponential averaging. Now, why do you want to change the number of averages per loop? Well, there's a trade-off here. The increasing number of averages, you get a tighter PSD, but less number of averages gives you a control that's more responsive, but with more variation. So you can see there's kind of this compromise. And again, we typically use 5 averages per loop as default. It's a good compromise between variation and responsiveness of the controller. And then once we take that stable average, we dump the control channel into this exponential factor and apply this weighting factor. The reason we use exponential weighting is it's a great way for the controller to learn how the DUT is going to react. So we start off at a low level, and as we increase it, the controller is going to adjust that drive signal based on nonlinearities and impacting and things that might be happening out on your test articles. You increase the force input. So this exponential averaging technique allows us to include previous averages in our current average so that we're not starting with a blank slate every time we do a control loop. And again, the weighting factor is very similar to the number of averages in terms of we increase weighting, we get less variation, but also less responsive. Again, there's some compromise position here where we get a good result. So degrees of freedom, again, this is a statistical evaluation of the confidence level we have in our measurements. And this degrees of freedom quantifies that statistical confidence in the PSD. Here's a table of degrees of freedom and confidence level of the results. Sometimes in random, you hear about kurtosis. It's a parameter that describes peakiness of a signal. What that really means is if you look at the time domain signal and you count the number of peaks and how many standard deviations they are away from your RMS value, and you plot those in histogram with a Gaussian distribution of peaks, which is our typical random vibration test, is Gaussian random, we get this bell curve distribution where pretty much inside of 5 sigma or 5 standard deviations, we have 99% of our peaks, and you have less occurrence of higher peaks the further away in standard deviation go. So the way kurtosis works is really what it's doing is adjusting the shape of this bell curve, okay? So that what we end up with is a more peaky signal. Why do we do this? Well, most real-world data is non-Gaussian, right? So if we're running a Gaussian random test, these two don't really look like the same. But with kurtosis control, we can increase peakiness in the time domain. An important thing to understand with this is you don't see kurtosis effects in the frequency domain, okay? Because we have the same amount of RMS energy going into this. It's the same amount of energy, so our PSDs are going to be pretty close to each other. But if you look at the time domain, you can see a kurtosis value of 12 has a lot more peaks than a kurtosis value of 3, which is Gaussian random. And here's just a histogram or bell curve of that, those different curves there. And you can see that Gaussian random has this typical bell curve distribution, whereas the increasing kurtosis values kind of flare out the end of this bell curve. Sigma limiting is also another thing that you run into with random tests. The origin of sigma limiting dealing with amplifier tubes. The original amplifiers used tubes, and they didn't like this random control because you get these peaks and you'd blow tubes in the amplifier. Now with steady state amplifiers that we have today, this isn't really much of a concern, but what sigma limiting does is make sure that we know exactly what the maximum peak is going to be that we're ever going to get in the time domain. This is important because we need to run this on a shaker. A shaker does not have infinite stroke or infinite force to it. So sigma limiting essentially clips the peaks to avoid having any type of DAC overloads going out to the shaker or any over travel that can happen. So if you think about this, right, if you have a 5G RMS test and you have a 5 sigma limiting, you're never going to get a peak in the time domain that's more than 5 Gs RMS times 5 sigma, or 25 Gs in the time domain. If we did sigma limiting up to, let's say, 8 or 9, you can see there's a significant difference there, right? So 25 Gs versus 40 Gs for 8 sigma limiting can be the difference between running a test smoothly and having an abort. Now, that 8 sigma peak is 0.01% of the time, so it's very statistically unlikely to happen. However, if it does, it can abort your test. So with Gaussian random distribution, 5 sigma limiting includes 99.9% of all the peaks that we're going to get statistically, and rejects any peaks more than 5 sigma, which statistically are unlikely to happen, but could potentially happen. We're basically just increasing certainty and capturing all the amplitude values. So I'm just going to go into the software and show a random test here. This is the random control software. Pretty straightforward. You put in your accelerometer sensitivities and select the right input modes and everything. You might be familiar with this already. It's just putting in the accelerometer sensitivities, and you can set ranges as well. And then random setup. You start over here, you input your frequency resolution, min and max frequency, degrees of freedom, and some of these other safety parameters and schedule parameters. We start at -9 dB. In this particular test, sometimes you start at -12, depending on how high a level your random tests are, and we step up. So we're going to go -9, -6, -3, and then our 0 dB level, spending about 10 seconds at each one of these lower levels to equalize before we go to the next level. And then we're going to spend 1 minute and 30 seconds at our 0 dB time. And the RMS level of this particular test is going to be 2.5 Gs RMS. To edit the reference profile, just come in here. Now I did something kind of fancy with this, is I just specified this plateau here and had 6 dB slope on either end. This is going to go from 20 to 2000 hertz, and it's going to have this flat plateau between 100 and 1000. We end up with 2.5 GRMS test. Okay, and then with our other parameters, we have maximum displacement here and all these other parameters that are going to give us an idea on whether our shaker can actually handle this test or not. So maximum peak in the time domain, 12.5 Gs. All right. If I go into advanced settings here, this is where you can see, for instance, the number of averages per loop and stuff. If I increase this, you're going to see it calculates what our absolute minimum control loop time is based on the number of averages per loop and the exponential weighting factor. So if I change that, all right. Sigma limiting is right here by default 5. We can adjust the actual type of signal here. Kurtosis control is over here. If we turn that on, we can put in a kurtosis value. Yeah, so some of these other things. This is an oversampling factor for throughput. This is about our measurements, whether we're going to use stable, exponential, or peak hold averaging. By default, we're set to stable. And our safety parameters basically are what's going to determine whether the test aborts or not. So once we have all that specified, and that should come basically right out of your test specification, we go into system identification and we can run a self-check. And basically what we're going to get is, you see settling, this is measuring our noise. Okay. Once we do buildup, that noise level is set, and we're going to start to ramp up that drive. And you can see this drive value and the responses. We can also look at that in the frequency domain. And the other thing that's good to always check is this coherence level. Coherence is a measurement of how alike input signal is to an output signal, and it is a value between 0 and 1. And what you want to see is very high coherence. This is an indication that we're going to get a good controllable vibration test. If you had a lot of dips in coherence or a roll-off in coherence, typically that's something wrong with your test setup that you have to check. Is your accelerometer loose or something? Or you can see, for example, here, my accelerometer at 0.7, which is at the end of this cantilever test fixture, you see there's a roll-off in coherence. Now, if you saw that on the drive coherence, you'd have to do some checking. But our drive coherence is great. And as expected, our coherence level at some of these measurement points is not as great. But that's okay, because these go into resonance. So we would expect that to not be like the drive signal. System verification, we have all these levels here of the peaks that we're going to see. But you can also go into system verification here and take a look at the response channels individually. So we can see, before we even start our test, where we might expect to see high response values. We can also take a look at the drive and see if that looks reasonable as well. If our initial drive looks like it might be too high, then we got to start looking at things like, is our accelerometer sensitivities input correctly, and things like that. How do you look at this and determine whether it's too high or not? Well, really what it boils down to is experience. You'll get a flavor for how these drive levels should be after working with the shaker. All right, so let's go ahead and run this random test and see what we get. Now, this might look odd to you, but really what this is a feature here. At our lower levels, we do not have aborts turned on, but our high 0 dB abort is always on. So this is the 0 dB abort level. So this 0 dB abort level always overrides. So now we're going to see our level starts to come up. Okay, so we're at -9 dB. And -9 dB, our RMS level is 8.9-ish. Now we've gone up to -6 dB. You can see that that top level abort is still the same. I'm also going to put, you know what, I'm going to hide this, and I'm just going to put our other responses overlaid on top. this measured PS. And now we can see all of our responses on top of our control channel. We got some nice resonances happening here. We're at our 0 dB level, 2.5 GRMS, and our elapsed time here. Okay. And of course, I don't have throughput running here, but if I did, you'd see this timer counting the throughput level. All right. And we can see here we're almost at our full time. And at that point, our test ramps down and we're all good. And then, of course, all this gets saved and you can view data in Navigator. So you can see under section 1 here, we have our random 2 tests that we just ran. And we can look at all the data in here. Or, of course, we can always go into batch printing and take a look at that as well. So batch printing is a nice little feature here to be able to dump out all this vibration data. We can take a look at all the curves. All right, well, that's my spiel, folks. And if you do have any questions, feel free to reach out to me. My contact info is here, and thanks for coming.